Hi again. So in this video we're going to look at what we will call Boyle's law. So Boyle's law is the relationship between pressure and volume of a gas. If we go to the learning intentions, then we'll see what we have to know about this. Looking at the 16.9, I can describe an experiment to verify Boyle's law, pressure and volume. And unfortunately, what we would have normally done is that you would have done the three of these experiments yourself. We have the kit in school, and because what you're often asked to do is you're asked to describe how the experiment works, describe how you would verify this relationship. So we'll eventually come up with a relationship. And so I'm going to use virtual flash physics, and I'm going to try my very best to give you the sort of realist sense of what you actually do in this experiment. And indeed, when we eventually go back into school, and which I'm assuming will be sometime at least, if it's after Easter, if it's before Easter, whatever, but we will get some time in school, then one of the things that we're definitely going to be doing is we'll run through these experiments. You'll know the theory behind it, you'll hopefully be able to describe what happens in the experiments already, but just so that you've done it yourself. And so 16.9, I can describe an experiment to verify Boyle's law. In addition to that, we're going to come up with a relationship, and I won't get too much into the relationship of that of here, but it'll be this one here, so P1V1 equals P2V2. But as I say, I'm not going to get too much into this just now, because what I want to do is for you to be able to describe the experiment of Boyle's law. So Boyle's law will look at the relationship between the pressure of a gas, and if you remember in the previous one, we can account for pressure as being the force that the particles, the force per unit area caused by the particles striking the container walls. And if we're looking at pressure, and we're going to see how volume would affect that. Now, as a very quick explanation in terms of kinetic theory, then if you reduce the volume, then you're going to have less space for the particles to move, and if the particles are continuing to move at the same rate that they're moving in, but you provide less space for them to move in, then common sense would dictate that they are going to make more collisions per second, more collisions with the container walls, and therefore the pressure would increase. And so this is something that we would expect. You reduce the volume, pressure increases. But here's an experiment to see actually to quantify that rather than just qualitatively describe. So we're going to quantify what happens when you vary the volume to the pressure. Okay, so the experiment that we have here is we have a container. The container is sealed. Inside there is a fixed mass of gas, so no extra gas can get in. We have a movable plunger where we can vary the volume. Connected to the container, we have a pressure sensor or a pressure gauge. This is what we would call a Bourdon gauge. But this will just measure pressure. And if you notice that we have pressure that is, the scale that we're using in here is times 10 to the 5 pascals. Now if we think about pressure of the air, so right here, sitting now here, the pressure, the atmospheric pressure is going to be around about 1 times 10 to the 5 pascals. So if we had, let me just adjust very slightly there. So the pressure here is going to be the same as the pressure in the atmosphere at sea level. And so right now, I'm sitting in a room, the pressure of the gas is atmospheric pressure, which will be 1 times 10 to the 5 pascals. What causes there to be a pressure at all? Well, the mass of all of the particles of gas in the atmosphere going right up to the very edge of the atmosphere, gravity will all push that down. And so gravity, if it's a spherical planet, then the atmosphere will be a spherical layer around the planet, and so you will have this equal pressure pushing down towards the surface of the Earth. And so this is what creates the pressure and the atmospheric pressure that we have. So what I'm going to do, I'm going to adjust the piston, I'm going to vary the volume, and we're going to measure the pressure. Really simple. So container set up that you can adjust the volume, measure the pressure, and so we start at 100 cubic centimeters and we can take it down to 90. You'll see that the pressure is increasing a small amount. We can take it down to 80. Again, as we vary the volume, we can read the pressure. So in this case, independent variable, the variable that we're going to change is going to be the volume, and we're going to measure the dependent variable of the pressure. So there we go, down to 50. Okay. So after running through the experiment, we have a set of data. So here we have the volume and centimeters cubed, and this is actual test data that we've got from the apparatus that we have in school. And so for all of the three experiments, the three different gas laws that we're going to look at, we actually have real data which was produced. I think it was produced last year by last year's National 5 class. And so we kept an example of typical results that we would get. Now, if you're doing this as an experiment in class, you would typically pick your different volumes and then you would measure the pressure, but you would repeat it another 2 times and work out the average pressure for this. In this instance, we only have one set of data, which is good enough just for the explanation of this. So we have our volume column, our pressure column. The volume is cubic centimeters, the pressure is times 10 to the 5 pascals. And so you can see as the volume increases, in this case, the pressure will decrease. And the first step to this is, and what I'm going to ask you to do now is to pause the video here. When you pause the video here, I'm going to get you to copy the table into, you have a choice, so you can either copy it into your jotter or a piece of paper, and then use a piece of graph paper if you have it to plot a graph of this. If you don't, then you can see a separate video on this, which will be a help video on creating a graph in Google Sheets, but you're to plot this in Google Sheets. So pause now, and once you've drawn your graph, we'll come back. And so your graph is drawn, and what we have is we have this curved line going down. And what it tells us that as our volume is increasing, so as the volume increases, the pressure decreases. And so the kinetic theory, as I said at the start of this lesson, kinetic theory backs this up, that as you reduce or increase the volume, then the pressure will decrease. But what we're interested in, rather than a qualitative description using kinetic theory, we actually want to quantify this. And we can't do this with this idea. So the standard thing to do when we have a downwards sloping curve is we're going to try and we're going to graph it in a slightly different way. And what we need to do in this case is to, if we take the inverse of the volume, and so if we divide each of these volume values, so do 1 over each of the volume values, and then we'll get this. And so we're having a new table, a new column of numbers here. And if we plot this column against the pressure, then we'll see what happens. Nicely, I've done one over here. We can now see that we have a different story altogether. So we're getting a pretty good straight line. Most points are on the best fit line, and we're nearly getting, we're not quite getting an intersect at the origin here. Again, if this was for something like the assignment or something like that, then we would need to take into consideration, excuse me, sorry, we would need to take into consideration that, and we would not be able to call this a directly proportional relationship. But for the purposes of this video, I'm going to say that it is a directly proportional relationship, although at this point it's proportional because it doesn't go through the origin. But what we're interested in is that it's directly proportional. The easiest way to show this is with using the course notes. And here's our original graph here, and we have then the manipulated graph with 1 over volume. We have a directly proportional relationship. The line of best fit passes through the origin. And so from this, what we can say is that pressure is directly proportional to 1 over volume, which would be written as this. From that, we can convert this into more of a mathematical formula. We can say pressure is equal to a constant times 1 over volume. Remember, this is this here, it would follow the equation of a straight line like this, y equals mx, where m is a constant value. M in this case is the gradient, but m is a constant value, so pressure is equal to a constant value times the x value axis, which is 1 over volume. And so pressure is equal to a constant times 1 over volume. Now, doing a bit of cross multiplication, if we just cross multiply the v to bring it over here, what we're left with is pressure times volume is equal to a constant value. And that's our mathematical relationship for Boyle's law. And that is really as far as we go with this. You have the description of an experiment. So the description of the experiment in the earlier part of the video. Again, there's some sample data there. But we have this here, and we finally have our formula. So that's the description of the experiment in Boyle's law. But then we have this other side of things, which is to calculate. We can calculate pressures or volumes using this relationship. And so next thing we'll do is we'll look at how we calculate values with these. So for calculations involving Boyle's law, what we'll typically have is we'll have two scenarios. So we'll start off with within Boyle's law's case, we'll start off with a container that has a certain volume, and we can call this volume 1, and we will be given a pressure of gas in there, so we can call that P12. And so, for example, we could have the volume 1, if we're calling it 100 centimeters cubed, and the pressure, well, if we say it was an atmospheric pressure, so 1 times 10 to the power of 5 pascals. And then what we would have is we would have the volume of this container has been reduced. And so let's say that the volume has been reduced and it is now at 60 centimeters cubed. We would call this volume 2. So we would write this down as volume 2. And so that would be 60 centimeters cubed. And the way of dealing with these problems, well, if we remember back to the course notes and the formula that we have, is we've got pressure times volume is equal to a constant. And if pressure times volume is equal to a constant, what this is basically meaning, and what we can do, is we can say that the pressure times the volume before is going to equal the pressure, the pressure times the volume afterwards. And so if we have our table, which would kind of look like this, we have pressure to here, that times that must equal that times that. And so we can write that in an equation form. And our equation, we would never usually, doing an equation, write that. That's just sort of the learning point. But the equation that we would have for Boyle's law, and if this was the question that we were trying to answer, we would then just write P1 V1 is equal to P2 V2. We make our substitution, just with the numbers. So we're going to have 1 times 10 to the power of 5 times 100. We don't need to worry about the units as long as they are the same unit. Okay, so if we're dealing in 1 times 10 to the 5 pascals, this answer will come out as 1 times 10 to the, well, as times 10 to the 5 pascals. And if this is in centimeters cubed, this is in centimeters cubed. So then we're just going to have P2 there, and then that times 60. Okay, we can cross multiply here, or we could choose to work out what this is before. And so just we'll do a couple, and then we'll see different ways of doing it. And so we'll just have 1 times 10 to the power of 5 times 100, which will be 1 times 10 to the power of 7. Is equal to 60 P2, and then P2 is equal to, it would just be that divided by 60. So 1 times 10 to the power of 7 divided by 60, which will give us this, which is 1.67 times 10 to the power of 5 pascals. Just like that. Okay, we'll do another example, and then I'll let you get on to do the questions in the course notes. And so in this case we'll have, we'll just start off with a container. It is like this, that the volume is going to be 200 litres. Litres is fine, as I say, whatever unit you're given at the start, you can just carry on through. So 200 litres, and your pressure is going to be, so 1 atmosphere. That's fine. And then we'll have, looking for a new volume here, and we can say pressure. The pressure after we've increased the volume, and we can say 0.4 atmospheres. Okay, exactly the same as before. We'll have P1, V1 equals P2, V2. In this case we're looking for V2, so we could rearrange in this case just now. And so cross multiply, get rid of the P2 by pulling it down here. So V2 is equal to P1, V1 over P2. Then we can make our substitution. So P1 is 1 times 200 over 0.4. And then 1 times 200 divided by 0.4. Oops. Going to give us 500. But 500 what? Well, we're looking for the second volume, and then the initial volume was in litres, and so it would just be 500 litres. And that would be it. Looking at the course notes, we have on a minute. Okay, so in the course notes, starting on page 14, again there's another worked example there, and then we have a number of practice problems. And so you should now, 5 of them in total, so you should now complete that. Okay, well that's Boyle's Law. Thanks for watching, and as ever, if you have any problems, please get in touch. Okay, bye for now.